Hey guys, welcome back. This is the second part of designing Twitter service. It took me some time to upload this video because first of all I was sick for almost 2 weeks, and then later on I didn't find enough motivation to upload the video. And that is why I would ask you to please like my videos and do comments on my videos, because your comments and your engagement actually motivate me a lot to upload more useful content for you guys. Also, I will be uploading my next video soon, and that video will be about designing Uber service. So if you like to get notified when I upload my next video, please subscribe to my channel and click the bell icon. Also, I would like you to meet someone. Actually, my 3-year-old daughter wanted to know what I'm doing in this Zoom. So, Sarah, can you say hi?
Hi.
Say subscribe to Baba's channel.
Subscribe to Baba's channel.
Okay, say thank you.
Say thank you.
Okay, so that's enough. Okay, now you can go and let me make videos.
Yeah.
Okay.
And then you can come back.
Okay, then I will come back down. Okay. Okay, say bye.
Me, I can. Bye.
Okay, go. Let's go. Go. So in the last video, we discussed first of all what are the functional and non-functional requirements of Twitter service. Then we discussed the high-level API design, and then we discussed the high-level microservice architecture of Twitter service. And we discussed that Twitter actually comprises of several microservices like the search service, tweet service, user timeline, home timeline, social graph, Fanout, and of course there's a data store and caching layer as well. In the last video that you can find here, we actually go deep down into designing the tweet service, the user timeline service, and the social graph service. In today's video, we will be discussing how the Fanout service works and how the home timeline service works, and we will also design the internals of the search service. So let's go. So now first we are going to design the Fanout service. The Fanout service is responsible for actually sending all the tweets that a user posts to the home timeline service of other users which follow that user, or also to the search service. If you see in this high level architecture of Twitter service, you will see that there is an arrow from the tweet service to the user timeline service. So what is happening is that when a user posts a tweet, the tweet service directly forward that tweet to the user timeline service. But tweet service uses the Fanout service to forward the tweet to the home timeline service and to the search service. So why is that so? Why are we designing like that? Why the tweet service is not directly forwarding the tweet to the search service or the home timeline service? Let me know in the comments below. What do you think? Fanout service is responsible for forwarding the tweets from the tweet service to search service and the user home timeline service. In case there are other components or microservices in the Twitter service architecture, for example notification or trending service, it is the Fanout service which is responsible for forwarding the tweets to those services as well. The Fanout service comprises of multiple distributed queues as follows. Whenever tweet service receives a tweet from a user, it passes the tweet to the Fanout service by calling an API exposed by the Fanout service, which is called push tweet. The push tweet API inserts the tweet in one of these distributed queues. The distributed queues at the first stage are started by the hash of the user ID of the user who posted the tweet. The function push tweet returns immediately after posting the tweet to one of the distributed queues. Now there could be multiple agents or workers who are actually listening to these distributed queues. These agents retrieve the tweet from the queue and then perform the following functions. First, they pass the tweet to the search service. Secondly, they query the social graph service to query the list of all the followers of the user who posted the tweet. For example, if there are 500 followers for a user, then they query the social graph service to retrieve the list of those 500 followers. And then they insert 500 messages in these distributed queues one for each follower. Third is they forward the tweets to any other services like trending service or notification service if they exist in the system. In our case, right now we only have the search service, so that's why they are all only forwarding to search service. But if there are other services like push notification or trending services, then these workers will be responsible for forwarding the tweet to those services as well. There are now second set of workers which are listening to this second set of distributed queues. These workers process the messages in these distributed queues and then forward those messages to the home timeline service. So these two sets of distributed queues can always start with minimum of, let's say, 3 distributed queues, and then we can always increase the number of distributed queues based on the load on the Twitter service. Also, if needed, we can always increase these worker agents as well. Now I have some questions for you. First of all, what do you think, whether these queues will be standard queues or strictly FIFO queues? Let me tell you the difference between the standard queues and the strictly FIFO queues. In a standard queues, the messages in a queue can be processed out of order. So it's totally possible that the message here could be processed before the message here. While in a strictly FIFO queues, the messages are always processed in a strictly FIFO, that is first in, first out order. Secondly, if we are using strictly FIFO queues, what will happen if we have to increase or decrease the number of these distributed queues and we have to reshard these distributed queues using consistent hashing? So we see right now whenever user sends a tweet, the tweet service call the push tweet API to pass the tweet message to the Fanout service. The Fanout service enter that message into one of these distributed queues for the tweets, and then later it queries the social graph service to receive the list of all the followers of that user who posted the tweet. And then as an example, if there are 500 followers of that user, then there are 500 records or messages that are inserted into this second set of these distributed queues. So now there's a question for you guys. What will happen if a user has million subscribers? What we would do in that case? So in that case, should we post a million messages here in the second set of distributed queues? What do you guys think? Let me know in the comment below. So I will ask you to pause the video right now and think about it, that how should we handle the case when a user posts a tweet who has more than 1 million subscribers. So the thing is, all those users who have a large number of subscribers, we can mark them as hot users. If you go back and check my previous video, you can see that we designed our user schema in a way that it also has a field called hot user. And we can certainly define any particular threshold that if the number of followers of a user are above that threshold, we can mark the users as hot users. For example, if a user has more than 10,000 followers, we can say that that user is a hot user. So for a hot user, we never insert the messages in the second set of distributed queues, because let's assume if a user has 1 million followers, then processing those 1 million messages will take like a large amount of time. If you go to Twitter right now, you will see that there are many users who have more than 1 million subscribers or followers. For example, Barack Obama has more than 110 million followers. So processing millions of messages in these distributed queues may take a lot of time and CPU resources and I/O, especially like network I/O, which means we won't be able to fulfill our latency requirements that we have discussed in our functional and non-functional requirements in the previous video, because it could take minutes to process millions of messages in those distributed queues. The tweets from the hot user will also affect the tweets from the non-hot user as well, because they all share the same set of distributed queues. So there's a question here for you guys. Let me know in the comment below what we should do in case of a hot user. If a hot user posts a tweet, should we insert those messages here in the second set of distributed queues or not? Now we are going to design the home timeline service. A user home timeline is a place where the user can see the tweets from all the different users which that user follow. So let's see how this home timeline service can be designed. The home timeline service is responsible for displaying the user's home timeline. This comprises of all the tweets from the other users which the user is following. The tweets are displayed in descending order of time. The design of home timeline service is similar to the user timeline service. The service comprises of application servers and distributed in memory cache. There is no data store involved in this service as we really don't need one. The home timeline is designed using a data structure which comprises of the hash map and a double linked list, and this double linked list consists of all the tweets from the other users which a user follow, and the maximum size of this double linked list is configurable. Let's say we are using the maximum size as 1000, which means that this home timeline for that user will actually will contain at most 1000 tweets from different other users which the user follow. The Fanout service calls into the home timeline service to insert the tweet at the head of the double linked list. This is an O1 operation. The tweets are stored here in descending order of creation time, with the latest tweet at the head and the oldest tweet at the tail. When the home timeline reaches its maximum limit of, let's say, 1000, then whenever a new tweet comes, we first remove the oldest tweet from the tail. The removal of the tweet is also an O1 or a constant time complexity operation. The home timeline service is a bit more complex than the user timeline service. In a user timeline service, we always insert a tweet in descending order of time. So we always insert a tweet at the head and we remove the oldest tweet. However, in home timeline, since the user is following many different users called followee, the service needs some mechanism to rank the tweets from different users. Let me know in the comments below what are the different mechanisms that the home timeline service can use to rank different users and different tweets from different users. Now we are going to design the search service. The search service is responsible for serving the user's search request, and the search service is comprised of following logical components. So we have ingester, search index, and blender, and of course we have data store with cache. The ingester or ingestion engine is responsible for tokenizing the tweet into a number of terms or keywords. Let me give you an example. For example, a user posts a tweet that Seattle is becoming hub of cloud companies. Eventually, the Fanout service will forward this tweet to the search service, and it will actually call an API to forward this tweet to the ingester. The ingester will first tokenize this tweet into following different terms. So, Seattle is becoming hub of cloud companies. It will then filter out those terms or words which are not useful to be used for search. These terms are called stop words or stop terms. So for example, it will remove is off becoming. So we see that the word is becoming off will be discarded now because they are not useful for searching. The ingester can get the list of those words, that is the stop words, either from some configuration or from some database that it has. The next step is to perform a process called stemming on the remaining words to find out their root word. Stemming is the process of reducing inflected or sometimes called derived words to their word stem or root word. For example, the root word for Seattle is Seattle. For hub is hub, cloud for cloud, but companies, this actually can become company. There are several types of stemming algorithms. A simple stemmer will simply look up the inflected form in a lookup table. The disadvantages are that all the inflected words must be explicitly listed in the table. New or unfamiliar words are not handled, even if they are perfectly regular. And the table may be large. For languages with simple morphology, for example English, table size are modest. But highly inflected languages like Turkish or Finnish may have hundreds of potential inflected forms for each root. There are other several stemming algorithms which I am not going to discuss here in this video. If you know some of the algorithms, please mention their names in the comment below. The ingester component then passes the tweet along with the root terms to the search index component. It is to be noted that the ingester would comprise of at least 3 application servers, and we can of course always increase these application servers as the load on the service increases. Why are we using at least 3 application servers? The explanation for this you can find in my previous video on designing tinyURL service, which you can find here. In short, in order for the ingester to be highly available, we are using at least 3 servers, and of course if the load on the system increases, then we can always increase the number of application servers. The search index component will actually create an inverted index. An inverted index is an indexed data structure storing a mapping between the contents such as words to its location in a document or set of documents, which in our case will be tweets or set of tweets. For the search index, the search index microservice or component stores the words along with the tweet ID in the following table in the data store. Now there are multiple approaches to shard this data store. The first approach to shard the data store is by sharding by words. In this approach, we shard the data store by the hash of the word, which means different words will be in different partitions, and then a single partition will hold all the tweets that contain that word. In this case, to find the tweets containing a specific word, we just need to go to a single partition. So in that case, the search is very fast. However, the call from ingester to the search index to generate this inverted index will be slower, because it's totally possible now that a tweet may contain 7, 8, 9, 10, 12, 13 or even more terms. So we would be going to different partitions to write the word to tweet ID mapping in all those partitions for all the different terms or words which a tweet contains. So in our example of tweet, where we are saying that Seattle is a hub of cloud companies, we have 4 different terms or words. So now when the ingester will send the write operation to the search index, we will actually go to 4 different partitions for the words Seattle, hub, cloud and company to store that tweet ID mapping to all those words. There are some other issues with this approach. For example, if a word becomes hot, then there will be lots of queries coming to this partition storing that word. In order to mitigate that, we can always add a cache in front of the data store, and we can also add a large number of replicas for that particular partition in the distributed cache. For more information about distributed cache design, please check my previous video on designing distributed cache, which you can find here. The second approach is shard by tweet ID. In this case, the write operation will goes to a single partition, and all the mapping between the words to the tweet ID will be stored there. With this sharding approach, the write operation is very fast because we are just going to a single partition. However, the search requires sending the request to all the partitions to read the list of tweets which contain a specific word. Then an aggregator server combines all those results from those different partitions before sending the final result to the user. The issue with this approach is that every single search query will hit all the partitions and thus will put extra pressure on the data store. The third sharding approach is two-level shard by words and the tweet ID. In this approach, we first perform the first layer sharding by the hash of the word to determine a group of partitions, and then we use the second layer sharding by tweet ID to determine the partition in that group where the word to tweet ID mapping should be stored. In this case, in order to search tweets for a word, we only need to go to only a small set of partitions. The search index will also have the same design, that it will have at least 3 application servers and also it will have a distributed cache and a data store with it. Now the third component is the Blender component. The Blender serves the search queries to the users on the Twitter platform. Whenever a search query comes to the Blender, it first determines the number of search terms. It then also performs stemming on those search terms to determine the root words for all those terms. It then uses those root words to run a search on the inverted index. If the search index is started by the terms of words, it can very quickly determine the result by just going to a single partition. However, if you are using the later approaches, that is either if we have shard the data store by the tweet ID or by the 2-layer sharding of word and the tweet ID, then it does a very quick scatter gather on the partitions or group of partitions for the search term in the search query by the user. Then it applies some more signals on the search results to refine the results according to the user who is querying the search. For example, it can figure out who is the search user, where he is, and what are his past interests, and based on that it can rank the results and present that refined search results to the user. The Blender also comprises of at least 3 application servers along with the distributed cache to keep the search results locally that it needs to present to the user. By keeping the search results of some search terms in the distributed cache, it can quickly serve other users as well when they query with the same search terms. So I'm going to stop my video here. Let me know in the comments below if the Blender needs to rank the search result, then how it can do so. Also let me know in the comments below how did you find this video on designing Twitter. And again, please do like the video and do comments if you find this video useful. Thank you and take care.